Yeah. I thought if it was a Monday, Wednesday, Friday class, the final exam was going to be on a Monday or Wednesday or Friday. It's on the, I mean, here, we'll just pull it up. It's on the main homepage. You'll find the list. See if we can figure out how to get there quick. So I think if we just type in like final exams or final exam schedule, so it's right there, the first link. And then it takes a little bit to read the chart. It's quite complicated. But let's, so we're here, let's get this right. So Tiffany is confirming that it's on a Thursday, and that's what I'd written down, but let's see. Okay, if your class meets for 1 hour or more on Monday, Wednesday, Friday, and starts between 8 and 10:50. Yeah, that's us right there. Thursday, December 20. Okay, apparently it's right. All right, so let's come back here. So we're on page 36. We'll take a look at the calendar. Today is day 2 of related rates. Next class, we have a couple of things happening. Number 1, we have a quiz, which means you're welcome to come here 10 minutes early to start early. Write whatever you want on an index card. Also, we have project number 7 due on what's today? Wednesday? On Friday. Any questions about that? Bubba. Yes. So when is your physics final? So you should check with Ted about that. All right, so we're on page 36. The plan for today is to do 4 related rates problems. How was the homework? I know it's spread out over 2 days, so it's okay if you haven't done all of it, but hopefully we've done some of it. How are we doing on these problems here? Tricky is, right? Yep, getting through them. It's lots of details. Right. It's lots of details. It really is. They're tough. They're tough. Certainly, a lot of these problems will remind you of some geometry things that you might have forgotten. You know, there's volume formulas and area formulas and things that they expect you to be able to pull out of a hat. So that's part of the difficulty. You know, like the volume of a trough. I don't expect you just have memorized, oh, the volume of a trough is blah. But what I do expect is that you'll recognize that the volume of this shape right here is just the area of the triangle times the height. Right, it's just a bunch of triangles stacked right next to each other. So the volume of that whole thing is the area of the triangle, the cross section, times 8 feet. That's the volume. All right. So let's see if we can tackle a few more of these problems, and then we'll see how much time we have left after we do these 4. So we're here on page 36, and we will go to part A, and we'll come over here to Chris.
If a snowball melts, so that surface area which is the diameter d, the diameter will confirm our result using mathematical snowball.
Okay, I appreciate that you said that very quickly. All right, so we've got a snowball here, and so we will draw our snowball. It's there, and it goes around. And the surface area, the snowball is melting, and the surface area is decreasing at 1 square centimeter per minute. So let's see if we can't start getting some symbols written down. So the surface area decreasing, that must be a rate. Can you guys write down some symbolic thing that has to do with that number 1? All right, so almost all of our rates in these problems are going to have d dt. And in this case, we have surface area. You call it A, you can call it S, whatever you want to call it is fine. What is it equal to in this case? Is it equal to 1? Close. -1. So yeah, you can put the units in, but it is decreasing. You get that decreasing in there with the negative sign. Okay, next piece says find the rate at which the diameter decreases. So we are looking for another rate. D dt equals question mark. What can we put in the blank? So you could put r. We'll have to do some translating at the end if we have a radius rate of change here. I'm going to go ahead and call it d. Doesn't bother me that there's a couple of d's up there in the top. That's the rate at which the diameter is changing. That's what I'm after. Capital D is okay. Yeah, capital D is fine. Okay, so let's see if we can't get some formula up here. All I know is that I've got the surface area. I have information about the surface area of a sphere. So that's the formula I'm after, the surface area of a sphere. So let's write it, surface area of a sphere. Again, this is one I'm not expecting that you just have memorized, but does anybody happen to know the formula? It's a reasonable attempt. So it turns out that the surface area of a sphere is 4 pi r squared. 4 pi r squared. Which is kind of interesting because if you get rid of the 4, what does pi r squared represent? The area of a circle. So somehow, if we had the circle that is that kind of equator there, if you had a solid circle going right through the middle of our sphere, and instead of just having one of them, you had 4 of them, and they were pieces of plate paper, and you could kind of mold it around. Apparently, we could perfectly cover the sphere with 4 discs, 4 pieces of paper that are exactly that kind of cross-section, the equator there. You'd have to cut it and rearrange the pieces, but apparently 4 of them would suffice to perfectly cover the sphere. So that's our surface area. And the next thing to do is what? You have your equation. Now what? Take a derivative, right? It is way too early to plug in that the diameter is 10 centimeters. Don't plug that in. We got to take a derivative. Although before we take a derivative, now that I realize that the problem asks for diameter information, but we have radius information here, it's in our best interest to translate this right now. We want dd dt. But if you take a derivative here, you're going to get the r dt. So let's change it before we go any further. So we know that what do we know? We know the radius is equal to half the diameter. And so I'm just going to replace the radius with half the diameter. So square the half, square the d, and then cancel. Questions on that manipulation? Okay, so now we've got our good-looking equation. What do we do to it? Now we take a derivative. I guess to make Chris happy, that should have been a capital D. Okay, and now I think we're ready to just plug in. Any questions on the derivative? right, how much is ds dt? -1. How much is d? It's 10 centimeters at this moment. Also make sure as you're doing the homework that you're aware of any unit conversions. There might be a problem where they give you something in inches and something else in feet, so just be aware. In this case, we have no problems. It's just centimeters. And that's it. So we'll just plug everything in. What's that? 0.16. Yeah, let's write the units just to be sure. So the units for a derivative are always the units upstairs over the units downstairs. What are the units of d? Centimeters per minute. So the snowball is melting, and at that one point in time, the diameter is decreasing, see the negative, by 0.016 centimeters per minute. Any questions on the process? So we'll look at a picture. I have an animation of this exact thing. But before we do, I just want to point out that, you know, like when I do these problems up here, there generally aren't false starts. I mean, we start and we write down exactly what we need to write down. Nothing extra gets written down. And I don't want to give the impression that it's supposed to be as clean for you as you are just starting to deal with related rates problems. Oftentimes you'll have false starts. Oftentimes you won't know, where's the equation that I need to pull out of thin air? Where does it come from? So I don't mean to give the impression that like it's supposed to be just, you know, start to finish, you should be able to do these things in one clean shot, you know, from beginning to end. It takes time. It takes time. Okay, so let's test our intuition. The surface area of this snowball is decreasing at a constant rate, 1 square centimeter per minute. So imagine the snowball starts out very big, and it's going to melt away, and it's going to become very small. So the question I pose to you is, what's going to happen to that diameter? Is the diameter going to get smaller at a constant rate, like a linear rate? Is it going to get smaller slowly and then speed up? Get smaller fast and then slow down? So thinking about intuition. So I had a couple of votes for slow then fast. What do other people think? All right, so let's have a look. This is another Wolfram demonstration. So there's our snowball, and we're just going to watch the snowball melt. And the first time through, it might be difficult to see, but I think the second time through, I'm able to see it's very slow in the beginning, and then very quick as it winks out of existence. All right, and then we've got all this other stuff happening. There's a lot of data here. The point we're interested in is when the diameter is 10 centimeters. So which one is that? Diameter, D versus time. So I think I need to get this number right here to be 10 if we're going to be at the right moment in time. So we'll get that as close to 10 as we can. That's good enough. And at that moment, we've got other graphs up here. This one has the surface area down at the bottom and the diameter here. Fair enough. And then surface area versus time. I guess the one we want is this guy right here, the d dt. I can't make it any bigger, I don't think so. I'm sorry for the folks. Oh, I can't make it bigger. I'm not sorry at all. So we come down here, and at that one moment in time, the diameter is changing at 0.02, which is a rounded version of that number that we got right there. And you can see from the picture that, what are we looking at here? That in the beginning, the diameter is changing not so much. You can see how flat this thing is, but then towards the end, it's changing quite a bit. You can see how it gets very steep here and becomes very big negative numbers. which matches the picture. Okay, so let's come back here and try part B, and we will go to Lindsay. Okay, lots of stuff happening here. We want to draw a picture, so there's my ground, there's my wall, and some random place in the middle of this, I'm going to put my little person. Just the stunningness of the detail. I mean, I impressed myself with that one. So there's the person, and then we got a spotlight that's on the ground. So we're going to put the spotlight, say over here. That right there is the spotlight, and we'll indicate it with a yellow. And then the spotlight goes up and hits the person and goes right across the top of their head in a straight line. And if we look at just this piece right here, what word can you use to describe that? What is that? That's his shadow, right? Because that's the part that doesn't get the light because he's in the way. So that's the thing that we're interested in quantifying. And I'll highlight this part up here because that's in the light. So just so we have a sense. All the stuff up above is lit, and then there's the shadow down below. And according to what Lindsay read, this person is walking from the spotlight towards the wall. So what will happen to the shadow? It will get smaller. As he walks towards the wall, the shadow gets smaller, yes? Okay. And you guys have seen this. Maybe you haven't done it against a wall, but if you're out at night and there's a street light up above you, if you are close to the street light, your shadow is pretty small. But if you are, as you get further from the street light, your shadow gets even bigger than you are, right? Same idea. If the sun is very low on the horizon, your shadow can be, 10, 20, 30 feet long. But if the sun is nearly overhead, your shadow is tiny. Same idea, just on the side. Okay, so let's see if we can start getting some of these measurements in. It says the light is 12 meters from the wall, so let's put 12 as this distance right here. The person is 2 meters tall, so we'll put a 2 next to them. And the person is walking towards the wall at a rate of 1.6 meters per second. So that means that means something. We can either give a name to this thing or we can give a name to this thing. It doesn't make any difference which one we do. I mean, one of them, they're both changing at 1.6 meters per second, right? This person's walking, and so it doesn't matter to me which one we label. Let's call that one right there X. But if you prefer putting X on the other side, that's fine. So can you symbolize that 1.6? It is a rate, it is a derivative. It deserves to be written down in symbols. What goes in the blank? X. X is changing at 1.6 meters per second. Nikki.
Why do they say to leave the bit of ground behind the person into X?
I just need to be able to write a symbol that says some derivative is 1.6. Something in this picture is changing at 1.6 meters per second. And if instead we had written X over here, it would look exactly the same. This thing is also changing at 1.6 meters per second. This one would be negative if it were on that side, because that one would be getting shorter at 1.6, while the other piece is getting longer at 1.6. But we need to give a name. We need to come up with some way to denote that something is changing at 1.6 meters per second. And so either of these line segments, the length of them is changing at 1.6. So I'm just giving a name to one side of it. If you don't separate them, I don't know. So we need something to be changing at 1.6 meters per second. So do you have an alternative that?
I guess I just wonder why we have as two separate segments as opposed to just one long, corresponding.
Right. I mean, it is one long piece that's 12 meters, but we need something to change at 1.6. We need to give a name to something that's changing at 1.6. And if you don't like it down there on the ground, we could say, okay, so here's a brand new line segment, and I'll just call that X, and that's changing at 1.6 meters per second. But we need to somehow relate the idea that it's 12 total, so that's the reason why. Okay, so we've got that, and then we're trying to find, I'll highlight this guy in green, find the rate at which the person's shadow on the wall is changing. So I feel like we need another letter. Where do I put another letter? On the shadow. We want the rate at which the shadow is changing. Okay, fine. Why? And as you do these problems, sometimes you'll label things that you don't need. Sometimes you won't have a label yet for something you want. And it just takes practice to get to a point where you're labeling what you need. And that's it. Okay, so we've got that. Let's symbolize what we're after here. There's a certain derivative that we're being asked to calculate. What goes in the blank? This is y, so this is dy dt that we're after. Dy dt is going to turn out to be negative. It's not clear yet. I mean, the only number we have as a rate is a positive 1.6, but yeah, dy dt had better turn into a negative number somehow. Okay, we need an equation that relates the x that we have information about and the y that we want information about. Some equation that relates the x and the y, and presumably the 2 and the 12 are also important in this problem. Any thoughts on where we might come up with said equation? Inverse tangent. So yeah, so let's talk about tangent first. So I like the idea of tangent because it incorporates the y and the 12. And maybe you could use another tangent one down here with the 2 and the x. I think that there's actually a possibility of going that route. Call this guy theta. You're going to write down two inverse tangent equations. You know that tangent of theta on the one hand is y over 12, right? But you also know that tangent of theta is 2 over x. Yes? Right, the smaller triangle. And it's the same tangent of theta in both cases. So I think what we could conclude from what Chris has suggested is that y over 12 and 2 over x are what? They're equal. They're equal to each other. We said a lot and didn't write a little. The idea that Chris had was to use tangent. So you can use tangent on the big triangle and know that tangent of theta is opposite over adjacent. Or in the small triangle, tangent of theta is opposite over adjacent. But it's the same tangent of theta. So we get that. Ernie had thought proportionality, but I don't think Ernie was thinking tangent. What were you thinking, Ernie? Right, and so the idea here is that these two triangles, the big one and the little one, are similar. Just like we saw similar, what did we see? Cones on Monday. Remember we had the drinking cone? And the actual cup itself was similar to just the cone of water at the bottom of that. And so, yeah, so we have similar triangles. And so things that are in the same place are in proportion. So the y is the vertical part and 12 is the horizontal. It's the same exact thing for the other triangle. So those are equal to each other. So I said earlier that I didn't expect you to know the surface area of a sphere. I do expect that you're going to be able to come up with, from out of nowhere, a similar proportion like we did here. I do expect us to be able to use similarity on a quiz or a test. Any questions on that? Okay, so I've got my equation, which means I'm ready to take a derivative. So let's go ahead and take a derivative of this thing. So y over 12, I don't want to use the quotient rule. What do I write first? 1 over 12, right? That's 1/12 of y. So the derivative is just 1/12. But what else do we need? dy dt equals 2 over x. What's the derivative? All right, so some folks, again, are getting a lot of use out of that one special case. Constant over x becomes negative the constant over x squared. If you don't know that one, use the quotient rule, or you could bring the x upstairs. There's lots of ways to get it. What am I missing? The x dt. Okay, and now we're going to plug some stuff in. So we have a 1/12. What is dy dt? That's what we're after. I really think it's worth our time writing that thing with the question mark, because then you don't waste any time spinning your wheels trying to figure out, oh, what is dy dt? What do I have to do to find it? You got to solve the problem. That's what you're after. So that's the last thing. -2 over x squared. How much is x? Let's see. So we're interested now in finally plugging in the 10 meters from the wall. So x is 10. X is not 10. But the way that we called x, we put x right over here, this purple. The guy is 10 meters from the wall. That's the thing we didn't name. So x is 2. Be really careful. So x is 2. So that's 2 squared down there. What is dx dt? 1.6. Okay, do a little bit of work and find dy dt. And once you've got dy dt, see if you can answer the other question, which I'll highlight here in blue. We want when the person is 2 meters from the wall, very close to the wall. See if you can get two numbers for these. Any questions on either of these two parts? Chris? -0.384. Did I miss here? -0.384. Okay. Right. And so as Nikki pointed out, we were expecting that the answer to these questions would be negative because the shadow is getting smaller, and it popped out. Where did it come from? It came from our derivative of 2 over x. You don't have to build it, but it's nice that the mathematics confirms what you expect the answer to be. And let's go ahead and get some units. What are the units for dy dt? Meters per second. Y units over t units. Meters per second. And so what that means is when the person is quite close to the light, the first part of the problem, the shadow is getting smaller at 9.6 meters per second. But when the person is just about on the wall, the shadow is getting smaller hardly at all, -0.38 meters per second. All right, so let's see if the animation agrees with what we got there. So here it is, person getting closer and closer to the wall. So a couple of things to watch. First, convince yourself that the person is walking forward at a constant rate. So do we buy that? There's no funny business in the animation. And then you can, what's that? Yeah, they're kind of gliding along. Yeah. And does the shadow on the wall do what we expected it would do? In the beginning, the shadow moves very quickly. It's smaller very quickly. And then as the person is close to the wall, the shadow hardly changes at all. Okay, any questions on that? All right, let's go on to the next page. So the next page, well, we'll get somebody to read it. We're not going to do the entire question here, but we'll at least think about it. Andrew.
Should A using an X radar
Okay, so like I said, I don't want to do this whole problem, but I did want to at least include one numerical example. So the first ship is the one that's sailing north. You can see that the x's are all 1.77, so here's 1.77, and then as time passes, 1.25 minutes, 2.5 minutes, 5 minutes, you can see that the y's are doing what? They're getting bigger, and so the ship is just here and here and here and here. So we know where the ship is at 4 moments in time. And then on the other one, ship B, you can see that the y is always 1.24. So let's put that somewhere, 1.24. And then what happens to the x's for that ship as time passes? They get bigger. And so we've got that ship is starting like way out here, and then it is somewhere at 4 different moments in time. And you can see that the two boats are at every moment in time, they're a certain distance away from each other. And so for example, at t equals 1.25, whatever the length of that line is, that's how far away they are from each other at that moment, okay? And then what happens to the line at the next moment in time? It's bigger. And then next one is bigger still. And so the question here is asking us about the rate at which those green line segments are getting bigger. Fair? Okay, so here's the idea. We're looking for some measurement of the distance between these things. And so how would you find the distance between 2 points in the plane? I mean, it is essentially the Pythagorean theorem. You guys know a distance formula, right? Distance between 2 points, remember it? Some big thing squared plus some other big thing squared, and that's the Pythagorean theorem. A squared plus b squared is c squared. And so I don't know what letters you guys are used to, but we'll try these. So that's the distance formula. And so what you can do in this problem is you can say that that each of these points here in blue, what's consistent about every one of these points in blue? The x is always the 1.77, right? So like every one of these points is of the form 1.77 comma something, right? Every point there, 1.77 comma something. And the purple ones all have what form? Right, because in each of the purple points, the y value is 1.24, the x is changing. And so what we can do then is start replacing things in our distance formula, square root of x2 minus x1. Well, I've got 2 points there. I've got the arbitrary blue point and the arbitrary purple point, and I'm just going to use this distance formula. So what should I put in my first thing squared? Yeah, so I'm just going to call it x minus 1.77. Good? Subtract the x's at those 2 points. Plus something else squared. Yeah, so 1.24 minus y is right there. Technically, you're supposed to subtract in the same order, but it doesn't matter because you're squaring it. Okay, so we've got a formula right there that relates the x and the y. And we're interested in the rate at which the distance between the ships is changing. That was the green line segments were all those distances. And so I don't want to go through the messiness of the calculation. You just have to take a derivative of that, and it's quite messy. But I do want to say this. At some point in the midst of taking a derivative, a dx dt will pop out. And a dy dt will pop out. Do you guys buy that? When you take the derivative of this thing, at some point, you get to take a derivative of what's in here. And what's the derivative of what's in there? Is 1 times dx dt. Right? It's buried. It's several chain rules in. But eventually, you're going to take a derivative of that green stuff in the parentheses, and the derivative of that is 1 dx dt. And at around the same point, you'll take a derivative of that thing. What's the derivative of that? -1 times dy dt. So in the middle of that massive derivative calculation, these two things will pop out, dx dt and dy dt. And we need to find them. And so that's the whole purpose that I asked this question, was just so that we would recognize that we can do numerical stuff. It doesn't have to be formulas given to us. So we're looking for dx dt at the moment when time is 5. So let's just focus on that one. The x dt at the moment when time is 5. Which one of the ships is the one that had the x that was interesting? Was it ship A or ship B? Ship B is the one where the x's are changing, right? And in fact, you can look at the purple point. That's the x. Okay, so let's look at ship B, and we're just focusing on this point right here when the time is 5. And I'm interested in the rate at which the x is changing. But all I have is this numerical data. So I've got the time 5 point. What's the next closest point, the next piece of information that I could use? Is the very next one, right? The 375. I've got those 2 points. If I wanted you to tell me the rate at which the x was changing as time passes, do you see it's a slope calculation? You've got 2 points right there. Dx dt represents a change in x over a change in t. What's the change in x? Yeah, right. Changes by 0.28. What's the change in t? Is the 1.25. That's our best estimate for this dx dt. So we're looking for, I'll write it this way first, change in x over change in t. It's just the slope, but it's not the normal delta y over delta x. It's these letters. If you did a regression, so regression on the one hand is good because then you're using all 4 points, presumably. But we are very narrow-minded as we approach this part because we are interested in the rate at which x is changing at just the moment when t is 5. And so in some sense, points that are far away from t equals 5 are irrelevant for us because it could be the graph could be doing some very strange thing around t equals 5 that doesn't represent like its general trend. But whatever it is, I'm interested in what it's doing at t equals 5. And so I don't want the general trend. It might happen to be very different from the point we're interested in. So I like the suggestion because it seems like it's better to use all the points instead of just 2. But we are very focused in the piece of information we're after here. And so the change in x is 6.08 minus 5.80. And the change in y, or change in t, I mean, is 5 minus 3.75. I think it's something around 0.2. Can somebody type that in for me? So I know we haven't done this one all the way through. All I wanted to get across with this thing is that if you have numerical data, you can still estimate derivatives. And I know it's been a while since we've done something like this. So maybe tonight, if you have some time, just go back to when we did numerical estimation of derivatives. And you'll see that we answered questions which just said, approximate the slope of the tangent line at this point. And here's a bunch of data in the table. And that's all that we did, is we just found the points that were nearest and did a slope. Okay, so one more problem I want to look at today is part D. No, I don't. I can bring it next time if you want. I haven't done it. I haven't done it all the way out. So maybe try to finish it. I mean, taking the derivative of that thing is big, but you have the tools to do it. So try to finish. And then we'll check answers next class. All right, part D. I'll go to Chris. Okay, let's give this a shot. So we've got our standard clock. And then we're interested in the moment when the time is 1 o'clock. I don't want to make it exactly 1 o'clock. I'll make it something near 1 o'clock, but I don't want to give the impression that it's fixed at 1 o'clock. So let's point the hour hand up there near the 1, and maybe the minute hand isn't quite, it's not quite up at the top. All right, so we're approaching 1 o'clock, but we're not quite there yet. And let's go ahead and label these two line segments. So we've got 4 inches and 2 inches. And then we're going to look at what we're interested in finding here. It says, how fast is the distance between the tip of the minute hand and the tip of the hour hand changing? So I feel like I need to draw something else in. I need to draw something to represent that distance. What am I drawing? Just that line segment that finishes the triangle. That's the thing we're after. The rate at which the distance between the tips of the hands change. And if I'm interested in it, what else should I do to make it easier to write stuff? We need a variable, right? Got to give a name to that thing right there. So let's give it a name. How about X? I was going to call it D, but then I thought of Chris. All right, we'll call it D. Okay, so I've got that. What seems unusual about this picture, this diagram so far, compared to all the other ones we've had? Ouch. Ouch. It's not a right triangle, so we're not going to be able to use the familiar SOHCAHTOA stuff that we've been using. Good point. How many variables are in this picture? 1. That seems like not enough to work with, right? We need to write an equation that relates the variables that are in the picture. And there's only 1 variable in this picture. So there must be some other fact that we can bring into play about a clock. I mean, there's... So here is something that I claim we can figure out. I claim that we can get some information about the rate at which that angle right there is changing. You buy it? Do you agree? What's that? We are working with time. Right. You know how long it takes for the big one to make a full revolution. You know how long it takes for the small one to make a full revolution. So you know lots of stuff about the angles of the clock hands, even if you haven't thought about it before. Okay, so now I've got 2 variables in my picture. And as Kevin points out, it's not a right triangle. So we can't use any of the familiar SOHCAHTOA stuff. But you guys learned in pre-calc some non-right triangle formulas. Can you guys think of something that, if you have an angle and 2 sides of a triangle? So we had a couple of general rules that we saw in calculus. We had 2 things. We had the law of sines and we had the law of cosines. And these 2 things are nice because they apply to every triangle, not just the real special right triangles. So law of sines, it said something like this. So the picture is just an old A, B, C, and then we can call, what am I doing here? Oh yeah, and then capital A, capital C, and capital B for the angles. Anybody remember what the law of sines says about the length of a side and the angle opposite? That's it. Right, that was the law of sines. And the law of sines was useful whenever you knew an angle and a side pair, the angle and the side opposite. Let's write down the law of cosines. I think this is what Todd was getting at before. So start it so that it looks like the Pythagorean theorem. That's the version that I'm able to remember best. A squared plus b squared is c squared. But if it's not, yeah, so that's a minus. 2 b, it's those same letters. Sine of c. And I think we're going to use that equation. And also, I would say this is maybe at the limits of what I might expect you to be able to pull out of the hat. You know, there's always this part of these problems where you just got to pull an equation out of a hat. For that one, that's right there at the border between I expect you to pull it out of a hat or I would provide it to you in a problem. Maybe I'd be sneaky and give you both sines and the cosines version, and you got to pick the right one. All right, welcome. This is a good day. Okay, so let's give it a shot. The angle that we have is theta in this picture, so I guess that means that the C that we're interested in is the X in this picture, right? The angle and the side opposite. So let's write that equation for this triangle. So instead of C squared, what are we putting? X squared equals. No, it doesn't matter which one. And let's clean this up just a little bit. X squared equals. Okay, good. Okay, we've got our equation. What shall we do with it? Take a derivative. How come it became positive 16? Yeah, cosine becomes negative sine. Right. Okay, so we've got our equation. I think one of our tables is pointing out that I never wrote down what we were after. So let's write down what we're after. We want the rate that the distance between the hands is changing. So symbolically, dx dt. That's what we want. Okay, so let's see if we can start filling in some of the blanks here. So I've got 2 times x. 2 times x. Can we figure out what x is? Because we don't know it. Like at the moment when we're at 1 o'clock, we're finally going to pause this video. How do I find what x is at 1 o'clock? Plug in something. Yeah. You got down here, this bottom red equation tells you what x is if you happen to know what theta is. Can you figure out what theta is at 1 o'clock? Sure you can. So let's write that. At 1 p.m., theta equals. One vote for pi over 6. One vote for 30 degrees. Who's right? You're both right. So theta is 30 degrees if you're a degree person, but we are calculus people, so radians. Ouch. Okay, so we know it's 360 all the way around, and there's 12 equal hours, so divide. All right, so we've got pi over 6, which means that you could use that last red equation right there and find x. X squared equals 20 minus 16 cosine of pi over 6. Find x. All right, so I'm going to guess 2.5. What is it? Woohoo! X is around 2 point what? All right, we'll go 2.48. Hey, that's pretty good. I know. I mean, it would be so much easier for me to. I could have just done this problem. I could have it written on the paper, but the fact is, I don't do the problems beforehand, so it's right. You know. Okay, so 2.48. That's how many inches apart the two hands are at that moment. So wonderful. That number right there gets shoved over here. 2.48. So we're still filling in this dx dt. Any, what is dx dt? That's what we're after, right? So this is where you reap the benefits for writing it down, so you don't try to figure out what it is. That's the end goal. Equals 16 sine of, what is theta at 1 o'clock? Still pi over 6. What do we still need to know? D theta dt. This problem now hinges on knowing d theta dt. If we can figure out the rate at which the angle between these hands is changing at 1 o'clock, then we're done, right? We just get to plug into an easy equation. So let's see if we can figure out d theta dt. Oh, are you doing that right now? Yeah, Ted and I should really work together more. What is d theta dt when it's 1 o'clock? And let's make this observation. T, the time unit, has not been given in this problem, and we're free to choose it to be whatever we'd like. So we can try to find d theta dt when time is measured in seconds, or minutes, or hours. Completely up to us, okay? So I've got a minute hand and an hour hand, so I'm not going to do this in seconds. If we use hours, then minutes become fractions. So let's use minutes so that we don't have the fractions. So we're trying to figure out how that angle is changing as time passes, time in minutes. So tell me whether or not you believe this. You could certainly find the rate at which the minute hand rotates around, because it rotates at a fixed rate no matter what time it is. And you could also separately find the rate at which the hour hand rotates around, much slower than the minute hand, but a fixed rate. Yes? Doesn't matter what time it is. Those two hands are independently rotating at exactly the same rate all the time. what can I do with those two rates of angle change to find d theta dt? What's the difference? Right? The minute hand, so pretend we're at 1 o'clock, the minute hand is going to try to catch the hour hand, and it's going to catch it pretty quickly. How long will it take to catch it at 1 o'clock, roughly? Little over 5 minutes. How come it's not exactly 5 minutes? At 1 o'clock, the hour hand is pointing to the 5-minute mark. Why does it take more than 5 minutes? Because the hour hand has slunk away just a tiny bit in the 5 minutes it took for the minute hand to get there. So all we need to do is find the two separate rates of rotation and then subtract them. And that will tell us how fast the angle here is changing. So let's give it a shot. So for the minute hand, it rotates at, I said we were going to do this in minutes. So how many minutes for one complete, so we got here radians per minute. How many minutes for one complete rotation? 60, right? The minute hand rotates all the way around in 60 minutes. So in 60 minutes, we have how many radians? 2 pi, right? 2 pi radians every 60 minutes. Great. Separately, the hour hand. Now you have choices here. There are a lot of different ways to write this number. What you could do is just put the same 60 minutes there because you feel like it, and then figure out how much the hour hand rotates in an hour. Or if you don't want that, you could say, okay, I'm just going to find out how long it takes for the hour hand to go all the way around once completely. Makes no difference. Like all of these fractions will be equivalent, just different versions of the same number. So what do we want to do? Yeah, I like putting a 60 in the bottom because, as Garrett said, what are we going to do with these two fractions? Then we're going to subtract them. So how about we just start with the common denominator now? So in 60 minutes, by what angle does the hour hand rotate? It's pi over 6. It's the same 30 degrees we saw before. The hour hand does pi over 6 radians every 60 minutes. So d theta dt is, and we just need to subtract those two numbers. So pi over 6 over 60 minus 2 pi over 60. Well, I suppose I'll do it in the other order. At some point, I'm just going to want a decimal. I mean, you can fiddle with this a little bit if you want. I guess it's 11 pi over 360, but really I don't want a decimal. I don't know, 0.09. Okay, what are the units here? Radians per minute. That's it. That is the rate at which the angle between the two hands of the clock is changing. 0.096 radians per minute. Can somebody multiply that by a 180 over pi, just so we get to degrees per minute, because I think we're more comfortable in degrees anyway. So multiply that by 180 over pi. Okay, so about 6 degrees per minute. If you were to sit here, if you were to measure the angle between the clock right now, it doesn't even matter that it's 1 o'clock or not. You measure the angle right now, you'll get something, right? I don't know what the angle is between these two, 40 degrees. And then I measure it 1 minute later. And what we just found is that the angle changes by about 5.5 degrees per minute. So if right now the angle is 40 degrees between these two hands, and I wait 1 minute, the angle between them should change by about 5.5 degrees. So it would be that down to about 35, because at the moment the hands are getting closer. Okay? So that is something that's true all the time, 5.5 degrees per minute. That's the rate at which the angle between the hands is changing at every moment during the day. Yeah, the sign you have to think about which, are we catching up or are we getting bigger? Okay, so then I think after all that work, we get to finally put right here, instead of d theta dt, 0.096. Positive or negative at 1 o'clock? It's negative, right? We said that just for the first 5.5 minutes or so, the angle is going to get shorter while the minute hand tries to catch the hour hand. So this one right here, we'll put C below. Lots of work down there to get that number. All right, so there's a little bit of work left to do. So can folks do a little bit of work on this? I'll highlight it here in blue. This is the equation you're after. You want to try to solve for dx dt using the calculator to get a final decimal at the end. Negative 0.155. X is measured in, what was it, inches? Inches per minute. So at 1 o'clock, the hands are getting closer to each other, the tips, if you're just to draw a line segment connecting them, the tips would be getting closer to each other at 0.155 inches per minute. Does that mean in the next minute the line segment will be 0.155 inches shorter? No, a minute is a long time to wait. This is only at the instant when we're at 1 o'clock. Nikki, is there a question about the calculation there?
I was wondering for a second whether looking at radians for one part was a problem and looking shifts for another part would be a problem, but I just...
Yeah, I don't think they talk to each other. I mean, if you want to, you could write down the units for each of the variable things in here, and I think everything will work out. You get inches per minute at the end. I think that would be super. So we've done this in the specific case when we're at 1 o'clock. We really didn't use the 1 o'clock very much in this problem, right? This rate of change, the 0.096, that's always the same regardless of what time it is. That's how the angle between the clock hands changes. So where did we use the 1 o'clock? We used the 1 o'clock right here in green to identify what the angle was. So if we just left it as some generic time, maybe this is a generic angle, you have to somehow come up with a formula for the angle depending on what time it is, and then that angle right there just went into the sine theta and it went into the calculation to find x. But I think it would be wonderful to see a graph. What are the what's on your axes? What are you imagining, Chris? Yes, as time passes, and then how long is that distance? I think that would be wonderful to see. Okay, so we have 1 minute and 45 seconds left to entertain each other. So let's take a look at a few more pictures. So here's one. So I'm going to try to, again, test your intuition. This person is another shadow one. Just the shadow is down here on the ground. This person is going to walk to the right at a constant rate. The question is, what's going to be true about the rate of change of the length of the shadow? As he gets further from the light, the shadow will get longer. But the question is the shadow going to get longer, slow than fast, fast than slow, or a constant rate? All right, so a lot of people saying slow than fast, okay, because extreme things happen when you're far away from the light. Let's try walk. Looking at just that black length, what does it look like? How does it look like it's changing? It looks, it's actually constant. Yeah, I know. Most problems we have are fast than slow or slow than fast, but here's one where it actually makes no difference how far away you are from a light post. So next time it's nighttime and you're near a light post and you have some dorky friends with you and a tape measure, what you want to do is just walk away from the light at a constant rate and see if you can look at your shadow, and it will get bigger at a constant rate. So that's fine. And then we have this searchlight thing. So here's the last question we're going to test your intuition about. The question is, all right, so you got this like stealth, I don't know what it is up here, it's going to fly to the left at a constant rate. We're interested in the rate at which this angle is changing, okay? The rate at which the angle is changing. So here's my question. Is the angle here going to change slow then fast, fast then slow, or constant? And then keep in mind, it's going to continue past the vertical, and so it'll be something else over here. Slow, fast, slow. All right, so it's going to be tough to watch, but let's just try to focus on that angle, fly. So it's going quick here, and you can't tell it's quick until you see how slow it is out here, right? Slow in the beginning, fast, and then slow. Next question, and I know we're out of time. I'm going to bring this down to 2,000 feet. It's still going to be slow, fast, slow. But how will the rate at which this angle is moving, how will it compare to the rates that we had before? More extreme. So fly. That's right. And so this angle is now whipping around here. It's changing quite quickly. And last thing, and then we'll call it a day. We'll just make it storm. And then, there we go. Yeah. All right. Have a wonderful day. We'll see you guys next time. Nikki,